Welcome to our deep dive into the quantization of charge and particles. Today we'll unravel why electric charge doesn't come in just any amount, but only in specific discrete units. This fundamental concept is at the heart of modern physics, shaping our understanding of atoms, molecules, and the universe itself. As we journey through this topic, you'll discover how the smallest building blocks of matter carry charges that are always whole number multiples of a basic unit. Let's start by exploring what we mean by quantization and why it's so essential to the world of particles. Quantization refers to the idea that certain physical properties like electric charge can only exist in specific fixed amounts. Imagine climbing a staircase. You can stand on one step or the next, but never in between. Similarly, charges don't come in random values. They're always exact multiples of a fundamental unit. This concept is crucial for understanding why matter behaves the way it does, from the stability of atoms to the flow of electricity in our devices. Let's see how this principle applies specifically to electric charge. Quantization of charge was first observed in experiments with cathode rays and oil drops. Scientists like Robert Millikan played a pivotal role by measuring the charge on tiny oil droplets suspended in an electric field. What they found was astonishing. Every droplet carried a charge that was a whole number multiple of a tiny fixed value. This discovery confirmed that electric charge is not continuous but quantized, forever changing our understanding of atomic structure. The heart of charge quantization is the elementary charge, denoted as E. This is the smallest unit of electric charge found in nature, carried by a single proton or the negative of it by an electron. The value of E is approximately 1.602 x 10 coulombs. All observable charges are intermultiples of this fundamental unit, making it a cornerstone of particle physics and chemistry. Protons and electrons are the primary carriers of electric charge in atoms. A proton carries a positive elementary charge, while an electron carries an equal but negative charge. This balance is what keeps atoms electrically neutral under normal conditions. The fact that their charges are exactly equal in magnitude but opposite in sign is a direct result of charge quantization. Neutrons, another key component of atoms, are electrically neutral. They do not carry any net charge, which means their charge is exactly zero. This neutrality is also quantized. Neutrons simply have 0 times the elementary charge. Their presence in the nucleus helps stabilize atoms, but they don't contribute to the atom's overall electric charge. Protons and electrons have charges of plus or minus e. Quarks, the building blocks of protons and neutrons, carry fractional charges. For example, up quarks have a charge of plus 2,3e, and down quarks have minus 1,3e. However, quarks are never found alone in nature. They always combine in such a way that the resulting particles have whole number multiples of the elementary charge. This preserves the overall quantization of charge in observable matter. Atoms are made up of protons, neutrons, and electrons. The number of protons in the nucleus determines the atom's identity and its net charge. In a neutral atom, the number of protons equals the number of electrons, resulting in a total charge of 0. This balance is a direct consequence of charge quantization, ensuring that atoms remain stable and predictable. When atoms gain or lose electrons, they become ions, charged particles. The charge of an ion is always an integer multiple of the elementary charge, such as plus 1e, minus 2e, and so on. This is another clear example of how charge quantization governs the behavior of matter, from the chemistry of salts to the flow of electricity in solutions. Even large objects like a balloon rubbed on your hair acquire charge in discrete steps. The total charge is simply the sum of many elementary charges transferred from one object to another. This is why you'll never find a balloon with a charge of, say, 1.5e. It's always a whole number. The quantization of charge holds true at every scale. Reason for charge quantization lies in the fundamental structure of matter. Since all observable particles are made from combinations of protons, electrons, and neutrons, or their quark constituents, and these particles have charges that are intermultiples of E, it's impossible to have a charge that isn't a multiple of this unit. This property is built into the very fabric of the universe. Alongside quantization, electric charge is also conserved. This means that in any physical process, the total charge before and after remains the same. Whether charges are transferred, created, or destroyed in particle reactions, the sum of all charges always adds up to an integer multiple of E. This law is a cornerstone of physics, ensuring the predictability of electrical phenomena. In chemistry, the quantization of charge explains why ions form with specific charges and why chemical reactions proceed in predictable ways. For example, sodium loses 1 electron to become Na+, while chlorine gains 1 to become Cl. The charges involved are always whole number multiples of E, making chemical equations balance perfectly. In physics, charge quantization underpins our understanding of atomic and subatomic processes. It explains why atoms are stable, why electricity flows in circuits, and why electromagnetic forces behave as they do. Without quantization, the universe would be chaotic with unpredictable interactions between particles. Robert Millikan's oil drop experiment was a landmark in proving charge quantization. By carefully measuring the charge on tiny oil droplets suspended in an electric field, Millikan found that all charges were multiples of a single value, the elementary charge. This experiment provided direct, quantitative evidence for the discrete nature of electric charge. Modern technology, from smartphones to computers, relies on the quantization of charge. The flow of electrons in circuits, the storage of data, and the operation of transistors all depend on the predictable, discrete nature of electric charge. Without this property, electronic devices would not function reliably. You might not realize it, but charge quantization affects your daily life. Every time you use a battery, flip a light switch, or charge your phone, you're relying on the fact that electric charge moves in discrete packets. This ensures that electrical systems work consistently and safely. Static electricity is a familiar example of charge quantization. When you rub a balloon on your hair, electrons are transferred in whole number multiples of E, creating a net charge. The resulting static cling is a direct consequence of the discrete nature of electric charge. Even dramatic natural phenomena like lightning are governed by charge quantization. The massive flow of electrons during a lightning strike consists of countless elementary charges moving together. Each electron carries exactly E, and the total charge transferred is always a whole number multiple of this unit. In conductors like metals, electrons move freely, but their charges are still quantized. When a current flows, it's the movement of many electrons, each with charge. This ensures that electrical currents are always made up of discrete countable units, not a continuous flow. Insulators, on the other hand, do not allow free movement of electrons. However, the charges present are still quantized. Any excess or deficit of electrons on an insulator's surface is always a whole number multiple of E, maintaining the universal rule of charge quantization. Semiconductors used in modern electronics also obey charge quantization. The movement of charge carriers, electrons, and holes in these materials is always in discrete units. This property is essential for the operation of diodes, transistors, and integrated circuits. Electrolysis, the process of using electricity to drive chemical reactions, provides another example of charge quantization. The transfer of ions at electrodes occurs in whole number multiples of E, ensuring that the products of electrolysis are always formed in fixed, predictable amounts. In particle physics, the quantization of charge is a guiding principle. All known particles from electrons to quarks have charges that are integer or simple fractional multiples of E. This regularity helps physicists classify particles and predict their interactions in high-energy experiments. Every particle has a corresponding antiparticle with the opposite charge. For example, the positron is the antiparticle of the electron and carries a charge of plus E. The existence of antiparticles further confirms the quantization of charge, as their charges are always exact opposites of their particle counterparts. Nuclear reactions such as fusion and fission involve the rearrangement of protons and neutrons. The total charge before and after the reaction is always conserved and quantized, ensuring that the resulting nuclei have charges that are whole number multiples of E. Cosmic rays, high-energy particles from space, also exhibit quantized charge. When these particles strike Earth's atmosphere, the resulting showers of secondary particles all carry charges that are integer multiples of E, demonstrating the universality of charge quantization even beyond our planet. Charge quantization works hand-in-hand with other conservation laws such as conservation of energy and momentum. Together, these principles ensure that all physical processes are predictable and consistent, forming the backbone of modern physics. Quantum mechanics, the theory governing the behavior of particles at the smallest scales, naturally incorporates charge quantization. The mathematics of quantum theory predicts that certain properties like charge must be quantized, matching what we observe in experiments. The standard model of particle physics is built on the idea that all fundamental particles have quantized charges. This framework successfully explains the behavior of matter and forces, unifying our understanding of the universe at the smallest scales. Symmetry principles in physics, such as gauge symmetry, help explain why charge is quantized. These symmetries require that certain quantities like electric charge can only take on specific values, leading to the discrete nature we observe. Some advanced theories, known as grand unified theories, attempt to explain why charge is quantized by unifying the fundamental forces. These theories predict relationships between the charges of different particles, offering deeper insight into the origins of quantization. Theoretical particles called magnetic monopoles, if they exist, would provide a natural explanation for charge quantization. Some theories suggest that the existence of even a single magnetic monopole in the universe would require all electric charges to be quantized. Physicist Paul Dirac proposed that the existence of magnetic monopoles would force electric charge to be quantized. His mathematical arguments showed that if even one monopole exists, all charges must be integer multiples of E, providing a theoretical basis for quantization. Modern research continues to explore the origins and implications of charge quantization. Experiments at particle accelerators and in astrophysics seek to test the limits of this principle and search for any possible exceptions, though none have been found so far. The elementary charge is one of the fundamental constants of nature, alongside the speed of light and Planck's constant. Its fixed value underpins the quantization of charge and is essential for defining units in physics and chemistry. Measuring the elementary charge with high precision is a major achievement in experimental physics. Techniques like the oil drop experiment and modern quantum electrical standards allow scientists to determine the value of E with incredible accuracy. The International System of Units (SI) defines the Coulomb, the unit of electric charge, in terms of the elementary charge. 1 Coulomb is equal to approximately 6.242 x 1018 elementary charges, reflecting the quantized nature of charge at the macroscopic level. Electric current is the flow of electric charge, and because charge is quantized, current is actually the movement of countless discrete electrons. This understanding is crucial for designing and analyzing electrical circuits, from simple batteries to complex computers. Capacitors store electric charge in discrete amounts. When you charge a capacitor, electrons move onto or off the plates in whole number multiples of E. This quantization affects the behavior of capacitors, especially at very small scales. Quantum dots are tiny semiconductor particles that can trap single electrons. The quantization of charge is directly observable in these systems, as electrons enter or leave the dot one at a time, causing measurable changes in electrical properties. In superconductors, electric charge moves without resistance but still in quantized units. The flow of charge is carried by pairs of electrons known as Cooper pairs, each with a charge of -2 e. This phenomenon is another striking example of quantization in action. Nanotechnology often deals with systems where individual electrons play a significant role. Devices at the nanoscale, like single-electron transistors, rely on the quantization of charge to function, enabling new possibilities in computing and sensing. As science advances, our understanding of charge quantization may deepen even further. New discoveries in particle physics, cosmology, and materials science could reveal more about why charge is quantized and whether there are any exceptions to this rule. Sum up, the quantization of charge is a fundamental principle that shapes everything from the tiniest particles to the largest technological systems. It ensures the stability of matter, the predictability of chemical reactions, and the reliable operation of electronic devices. Understanding this concept not only deepens our appreciation of the universe, but also empowers us to harness electricity in countless ways. Thanks for joining us on this journey through the quantized world of electric charge.